okay? And of course, volcanic hydrothermal systems, they evolve with time. They are influenced by the magma heat that will slowly cool and crystallize with time, of course. They are influenced by permeability and how the water is circulating. And then, of course, by lots of chemical reactions. They're pretty on the surface, okay? So I guess I was drawn initially to these things because I liked going there, and usually after a long day in the field, you could always have a hot bath or something. So this was really nice. You have often these intensive, colorful, altered grounds and hot springs. Sometimes you have steam vent, which is almost just pure steam. Sometimes there's more volcanic gases, and then you have characteristic, all kinds of sulfur and sulfates and all kinds of things on the top, and a much more like an acid vapor phase. And they are, of course, hosted by many geothermal power plants. So this kind of hydrothermal systems, they are harnessed for its hot water, both to generate hot water for heating and cooling today, all kinds of industrial processes, greenhouse farming and so on, but also to generate electricity. And this is quite nice because many of these systems, they're drilled down to deepest holes are maybe 4.5 kilometers, but typically they're maybe 2 to 3 kilometers, and you can collect samples at depth if you might know the right people, so to speak. But because these are always operated by some companies that they don't really like scientists to walk around there. Anyways, so the hydrothermal fluids, most of them are close to be pure water, okay? So I didn't want to put a number there, but most of them are 99.9+% water, okay? So they're a little bit different from a volcanic gas, which is maybe less water, even though the water is dominant. And this is typically the Taupo in New Zealand and Yellowstone. I mean, many of you have come to Yellowstone, Iceland, and many, many other places. Sometimes you have quite significant CO2 in the systems, maybe 1 to 5, 10 mole%. This is not common, but this is kind of, you see this in Italy, Turkey, some places in Central and South America. And it's kind of just pure water and loads of CO2 in a way. And then we have brines, okay? And maybe the brines have been not so much studied because they're complicated. And you have typical brines that are kind of modified seawater. That would be roughly, you would say, 0.67 mole% salt, 3.23 weight% salt. But sometimes they're much more complicated. It's not only sodium chloride. They can be like a mixture of sodium chloride and potassium chloride and calcium chloride, magnesium chloride. And these are sometimes up to 10–15% salt. And they're kind of not so much utilized for obvious reason. But I mean, you can see this in fluid inclusions and so on. And you saw some of this sampling. I mean, we collect samples at surface into these gas sampling bottles you saw earlier today, but we also collect samples from liquids and steam and vapor from boreholes. This is wonderful. And then, of course, people look at fluid inclusions, and sometimes it's a volcanic gas. I usually don't throw up a table at a talk like this, but I thought this could actually be quite useful here. So I cleaned most of the elements. It's in a geothermal fluid, you find the entire periodic table, okay? But the fluids are usually kind of around 250 to 350 degrees. They're dominated by liquid water under pressure within the subsurface. They have close to mildly acid to mildly alkaline pH value. And remember, this is pH at the temperature, and neutral pH is maybe around 6 at this temperature. they have quite a lot of silica, variable salt like a sodium chloride, but usually not so much. I mean, Montserrat, which is in the Caribbean, that's kind of a modified seawater. There is CO2. You definitely have this volcanic volatile input, CO2, sulfur, etc. But they are much lower than if you look at the to your right side, the volcanic gases. I mean, I took two examples. Vulcano, Italy. I like going to Vulcano. There are fantastic restaurants there. But you can see it's about maybe 85 to 98% water. The rest is mostly CO2 and considerable sulfur. I took the new Reykjanes emissions, and this is at 1 bar because we are sitting at the surface, and you can see it's quite similar. So you can see you go from a very enriched volatile CO2 sulfur systems of the volcanic gases, and then to some kind of diluted signals in the hydrothermal systems, plus lots of the rock forming elements, and sometimes salts that are kind of related to the source fluid, seawater, rainwater, and so on. Then in the yellow, this is the new front that many of us like. This is the interface between the magmatic heat source and the conventional convective or circulating hydrothermal system. And these are kind of superheated steam to a supercritical water, depending on how you want to define it. We just call it today super hot, which is not very a rigorous definition. And you can see that what is slowly happening, it's kind of many of the rock forming elements are disappearing, whereas still as the volcanic volatiles, they're still in the fluid. But these mostly are usually dominated by the groundwater source rather than the volcanic source. Okay, so I'm going to use the next about 10 minutes to go through a little bit what is available in order to understand reactions and sources and so on of different things happening in these systems. And the way this is often done today is that there is kind of a two-level of modeling. One is related to fluid flow and heat transfer. So there's a big group thinking about that. You can, I mean, technical word would be thermal hydrologist, I guess. And then on the top of this, there is some kind of a fluid rock interaction. You are somehow cooking up the surrounding rocks and minerals by this hot moving fluid. And then you have volcanic gas volatiles going into the bottom of these hydrothermal systems. And sometimes the gases go through, sometimes they are scrubbed and dissolved in the hydrothermal fluids. This depends on the flux. And then you have temperature and pressure all over the place, okay? And usually the modeling is like, as I said, in two levels. It's a heat and mass transfer modeling, okay? This is the hydrology part. And then is what we call a geochemical modeling. This is you're trying to model the gas fluid rock interaction. And sometimes this is incorporated into the same modeling framework, and we call that reactive transport modeling. And that's kind of a voodoo thing. Okay, you put something in, you press run, and 2 weeks later you come back and you have no idea what it means. but it's available, okay? Usually the way this is used, I don't have time to show too much about that. Usually is that you study a particular process or a hydrothermal system or many hydrothermal systems for the same process. Then you collect samples like we saw this morning, and you analyze the gases and the liquids and so on. Sometimes we can have subsurface cores and drill cuttings for mineralogy. And then you try to put everything together, and then you model it, and then bingo, you have a nice story. Okay, so the models, they usually never stand alone. They are always anchored to some real data. And I guess I need a half an hour to talk about those. But There are many modeling platforms available. Some of them are free. Some of them cost money. Some of them have an industrial focus, and some of them have purely a scientific and academia focus. So the Freak-C, which is purely a geochemical modeling platform, there is a little bit hydrology. It's aimed for lower temperature, but you can model geothermal conditions like up to 350 degrees. There's Tough React, that's a Berkeley program. That's a reactive transport program that goes up to 350, 400 degrees. There is the geochemist workbench, which is actually very nice, but it costs lots of money, and it's used maybe more related to the industry. There is GEMS. I think there's a workshop now on how to use GEMS. GEMS is actually a very powerful program because it solves the set of equations in a different way. It's a freeware. It's initially developed through nuclear waste, and we use that quite a lot. GOT, which is purely a hydrothermal program. It's a Lawrence Livermore program. CSMP++, that's an ETH initial platform that is all over. We run that like crazy, but this is maybe more on the heat and the fluid transport. And then this can be coupled with some of like the GEMS or Freak-C and so on. And now it's this appearance, like you saw this morning, of endless Python codes that kind of work, but you need a special course sometimes in order to know how to run it. So we have many like an isotope platforms. We do also isotope modeling on the top of this, and they are all written in Python. Okay, so I'm going to give you two examples of how this modeling is done and what type of information we gain out of it. And I took two examples that are maybe interesting to volcanic hydrothermal interface and then volcanic degassing processes into hydrothermal systems. So the first one is this formation of superhot fluids that is kind of an envelope just around the magmatic heat source. It's a boundary that you go from kind of a conductive heat transfer into like a circulating heat transfer of the hydrothermal system. The thickness of this is something we don't know. We have drilled into this in practice by accident, and now there are some programs in Japan, New Zealand, Mexico, in the US, Iceland, Italy, to drill into these high energy fluid sources. But what I'm going to show you is just going to show you how a heat and fluid transfer modeling would look like, and then adding a thermodynamic silica solubility model on the top, and then couple the two to see how silica actually being transported and precipitated in a volcanic hydrothermal system in the vicinity of this. The second one is sulfur gas scrubbing. So what happens if we have SO2 coming into the hydrothermal system? How do we all model all these reactions and minerals that form? And I'll show you some basic stuff. This is purely a reaction modeling platform that's maybe of interest to you. There's no like circulation going on. We did this for sulfur isotopes. I don't have time to talk about that. And that's kind of Python routines. And then we just see how the fluid chemistry and mineral evolve as a function of if we have a lot of water-rock interaction, high SO2 flux or a low SO2 flux. Okay, so now I'll be quick. So this is often how these hydrology models look like. They run as a function of time. There's a permeability constraint. There's a full equation of your water, sodium chloride. This is pure water. Now we have also water CO2. This is after 2,500 years. This is our initial intrusion. This one is placed at 2.5 kilometers. This one is placed at 5 kilometers, just to show you the difference. The blue thing is what we would call a conventional hydrothermal system. This is like a subcritical liquid type fluids, okay? And this pink one is the superheated fluid. Depending on the pressure, this would probably be superheated steam. This is something we would call a supercritical fluid. Okay? All the funny shapes and so on, I don't believe any of those, but I mean, they look nice. So you can see that the heat of the intrusion that is in place is heating the groundwater, and there is kind of a circulation going on. And this is kind of a projected flow vector. There are like thousands of this flow vector going on. And you can see that you're drawing down kind of a non-thermal groundwater initially, or less than 100 degrees. You're heating it up, and then it's shooting up towards the intrusion. If you look at a phase diagram of water, and maybe you're not used to look at phase diagrams like this would be pressure. This is temperature projected here, and this is the enthalpy of, okay? So this would be liquid field. This would be the two-phase field of liquid coexisting with steam. This is something we would call superheated steam, and this is something we would call a supercritical fluid. But the super hot, we talk often about it, but it's just defined by the critical temperature. So these projection lines I was showing here, which I think is quite useful to think about the systems. These vectors are then projected on the phase diagram, and you can see what happens. You go from a liquid, different lines means different permeability and depth of intrusion, deep intrusion, shallow intrusion, and you can see they're always heating up from really ambient conditions, and then they are superheated while the superheated conditions or supercritical conditions, depending on how you look at it, and then they flow up to the surface, they go through the two-phase field, and eventually they're released. Okay. If you look at some mineral solubilities, this would be quartz. You go from a low quartz to a high quartz solubility, and this is in moles per liter, to a medium to a low. So you see what's happening. You go from solving your silica, precipitating your silica, to kind of resolving your silica. And if you put this all together, and bingo, this is where our model looks like. So it's basically just a thermodynamic modeling on the top of a heat and mass transfer modeling. This is your dissolved silica. You see it goes from low to high to low. And remember, they were circulating like this to high. And then if you're sucking high to low, this is the projection. This is where all the silica is going. So this means that somehow in a hydrological cell, you will have a lot of silica precipitating at the superheating or the superhot fluids that we see. So you see this? Well, next question. We're not sure. Okay. The second, so this gives you an idea how this is coupled. Of course, you can do this for all kinds of elements. And this is often done for like a metal, porphyry, epithermal evolution, and so on. This was the initial interest. But I mean, this is also being done for just the hydrothermal system that is studying. Just one example. Okay. Second example I want to give you is volcanic sulfur gas scrubbing into the hydrothermal system. You have your magma. You have magma degassing into the overlying hydrothermal system. The pink one is the superheated plume, mix. And then within the system, you have a fluid water reaction. Okay? That's the most simple thing. And if you think about what reactions are potentially happening with a sulfur volatile phase from a magma degassing intrusion, you have predominantly acid being sourced, and then you can drive all kinds of redox reactions going into hydrogen sulfide, sulfuric acid, elemental sulfur, and minerals like anhydrite, pyrite, alunite. You can just name. So a typical reaction modeling like this would involve maybe something between 100 and 500 reactions like this, and we're just modeling all of it, okay? And it's not complicated. The only thing is you have to find out what is your variable. Is the variable how much SO2 there is going into the system? Is the variable the extent, how far these reactions are going? So there are often multiple variables. So what I'm going to show you is like a high SO2 input as a function of time, and then a low SO2 input as a function of time. And I'm just going to show you how these reactions evolve. Okay. So the first one, that's SO2 gas spreading where there's a high magma gas flux. Okay. So what is that? Come on, it's just you turn it on until you see some trend, and you kind of see that there are always two trends. There's a high and a low flux, and then there's a turnaround. So what you have here is an SO2 going in at the high flux, okay? What happens is that the system becomes dominated by SO2. It's just flowing through, okay? Sometimes we call this like a more of a volcanic gas-dominated system with a hydrothermal envelope on the sides, because on the side there is a mixing, and then you have maybe sulfate forming, and a little bit H2S, right? So typically you will have the SO2 dominating and some significant H2S, and sulfate also being important. The fluids are acid pH, and with progressive fluid rock interaction, you get this typical algae type of. And this is kind of how it looks like. So this would be a high flux as a function of how much rock you have reacted, okay? And you can see that it's mostly SO2, then the H2S, SO4, the pH is 1, okay? And then, well, there is a turnaround. You see, you get the mineralogy as well. You can see you have dominant the element of sulfur, aldehyde, sulfide, chlorine, anhydride, actually anhydride from that's it. And then there's a completely different mineralogy. We have this turnaround. Okay. 2 more minutes or 1 more minute. If you have a low magma gas flux, okay, now we just turn the SO2 down, and what is the physical meaning of that? Of course, it's just it can be slowly degassing and alter intrusion or something like this. And then what happens is you develop kind of a hydrothermal dominated system where the SO2 flux that is much lower is eaten up and reacted and neutralized by the rock forming reactions. Okay, and you go to kind of H2S and sulfate being the dominant. pH is near to neutral. If you remember all the things in the table there, it's like this. Okay, and then you have kind of a typical epithermal type of. You have alpite. You have quartz, chlorides, calcites, and things like this. Okay, and then of course there's much more, but I mean it's how it works. And then when you look at the systems, like we saw some pictures of white diamond, it's a typical like a high SO2 flux systems, and you kind of see the sulfur going through with a much higher temperatures, and then you have a hydrothermal envelope. Where there is a hydrothermal system, this is kind of low sulfur, low CO2, you go into more like a thermal ground-water system. You don't want it for hot springs where the sea goes. Okay, so I'll stop here. So many modeling platforms, gave you 2 examples, endless thing you can do. The next step is actually trying to couple the volcanic part of the modeling with the hydrothermal part of the modeling. Okay, thank you.
So we've got time for a few questions. Yep, Lily.
Just you want to tell
Can you just push the gray button there?
The gray button, I have no idea. Oh,
Yeah, yeah.
How well do the different modelling platforms agree, given what we've seen with the other models? Like, does it matter which one you use? Have you got massively different results?
they kind of all do the same thing, okay? But most of them are solve the same equations. The differences in the geochemical modeling would be what is included in the model in terms of a database, thermodynamic or a kinetic database. And then for the heat and mass transfer modeling, they're kind of usually the same. They solve the same equations, okay? So it doesn't matter which one you use, actually.
I was wondering if you could comment on the calcite and with how that fits with the natural systems that you're looking at, please.
Yes. So you mean, yeah. So you mean if you form calcite or if you don't form calcite? Yeah. Okay. Yes. Yes. So most commonly you don't see a lot of calcite in these hydrothermal systems. If you see calcite, they're usually related to the upper kilometer of the systems. And it is thought to, or the explanation, it's related to decompression, boiling, and phase separation, and changes in pH and speciation rather than anything else. So calcite usually in the bottom of these geothermal systems, it's absent. And the carbon content in the rocks is usually below what is in the fresh smelts. Yeah, that is more to do with the pH in your model than anything else. Yes, yes, yeah.
Yeah, I had a question. We're actually doing pH1 experiments.
Yes.
Where we flush fluid and an SO2 CO2 mixture.
That's wonderful.
And our pH goes up by a little bit, but it doesn't go very far because it starts to seal with alunite and hydrite.
Yeah.
And maybe a couple other things.
Yeah.
So my question actually is around the kinetics of what you can model. So you're showing everything presumably in equilibrium, but actually you could argue, and even in our experiments, we can't get to that higher pH because the whole system is sealed completely.
Yeah.
So do you have any kinetic constraints?
So sometimes these models are purely run, as you said, like an equilibrium thermodynamic model. But sometimes there are kinetics. In the model I showed you, there is no kinetics. But sometimes we do kinetics. But this is very computationally demanding in a way. Okay. And for some of the kinetics, they're just poorly constrained. Yeah.
We hopefully will constrain some.
Yeah. But they can be written in.
Yeah,
definitely.
John, let's go to the last one from John.
Oh no, that's just me telling people to have questions to put them on chat.
Oh, okay.
Go, John.
In your first example of the superhot fluids,
yes,
is there a relationship between silica precipitation and cracking or fracturing? And if so, can that be modeled?
Yeah. So the answer to that is no, it's not written in the current code. So any rock mechanics is missing in a way, but this is one of the key things. Okay, definitely. So these are kind of all ideal cases to gain insight into what you think is going on rather than to say what is exactly going on. Yes. So this is why I said they are to increase or decouple. Sometimes also we use it to decouple different things. Okay, the permeability, cracking versus sealing versus something like that. You can do that, but you'll have to do it by hand in a way. You have to change physically the permeability in these models.
I think there is a way potentially tough reactors coupling with tough modeling. So there is a way in which it's feeding into the physical process.
Yeah.
So you take the reactive transport to get the mineral signatures, and then you can feed that into, let's say, deformation or pressure.
Yes. Yeah.
And I think that's when we can couple with more of a rock mechanics understanding of how these silica saturated or sealed systems might behave. And then we can look at cracking.
Yeah.
That's probably a our best chance. Anyway.
Absolutely. The other thing is actually to couple like a magma, pluton, or intrusion cooling process with a hydrothermal cooling convective process. And we're trying to do that now, but I mean, it's also just a process model.
Let's talk about it.
Okay, thank you.
So much.
Yeah.